It's my pleasure to introduce today's speaker, Professor Danna Freedman from MIT. Danna received her bachelor's from Harvard and her PhD in chemistry from Berkeley, where she worked under the direction of Jeffrey Long. She spent a few years as a postdoc in the lab of Dan Nocera at MIT before beginning her independent career as an assistant professor at Northwestern, where she ultimately was promoted to full professor. And over the past year or so, maybe even the past few months, Danna has moved her lab to MIT, where she is currently the F.G. Keyes Professor of Chemistry. Danna has been a recipient of too many awards to list here, but recent highlights include the 2019 ACS Award in Pure Chemistry, as well as not one, but two presidential early career awards for scientists and engineers. I think her talk will be a refreshing change of pace for the seminar series, since she can offer us a window to the more chemical side of quantum information science. And in particular, her lab is well known now for synthesis and development of designer molecular spin qubits. So please help me welcome Danna. Take it away.
Thank you so much for the kind introduction. Yeah, the two PCASE awards is actually a little bit funny. You're not allowed to win two of them, but the federal government made a mistake. I let them know immediately that they made a mistake, but they thought it was best to just give me two awards rather than acknowledge the error. So I technically get two awards, but the second one doesn't have money attached to it. So that I think makes it okay. So I'm really excited to get to speak to this audience about our chemical approach to quantum information science. And I know that this is an audience that is deeply embedded in the field of quantum information science, but I'd still like to take a brief step back and discuss how I, as a chemist, see quantum information science and the role of chemistry within it. So if we think about quantum information science, I think of it as a way that our scientific society, largely physicists, can take our control and understanding of the quantum nature of the universe and bring it to bear on a range of applications. And of course, quantum computation is the one that's been the most popular, but we also have applications like quantum sensing, quantum communication, quantum metrology, et cetera. And so what I want to highlight with chemistry is chemistry enables us to make systems that are atomically precise, reproducible, and tunable. And so I think that it would be a little bit silly to think that the same system that would be ideal for a quantum computer would be ideal as, for example, a universal quantum sensor. And quantum sensing is a great example of an area that would benefit from tunable, customizable systems. So there are challenges like measuring a small magnetic field, where having something super tiny that you can put directly on a surface would be really powerful. Or challenges like the one I've depicted here, measuring the membranes or measuring spins perhaps near a cell membrane. And in all of those, being able to design and tune your systems has a lot of power. And I also want to just remind everyone, I know that we think about this all the time, but sensing is inherently an analyte specific activity. And so the ability to tune your sensor towards different analytes has a lot of power. So with chemistry, we can design systems both for different analytes and for different environments. For example, you can imagine imbuing a molecule with water solubility or making a molecule planar so it can interact with the surface of a magnetic material. Molecules also have a lot of potential for areas like quantum communication, where tunable emission frequency, for example, could be very valuable. Now, there are many people in this audience who are experts at far more established candidates for quantum information science than molecules. And so I do want to be very clear. What I believe is that we should have a huge tent and that there are going to be many different pathways to success in this field. So let's talk a little bit more about why molecules are awesome. And to do that, I'd like to take a step back 20 years ago to one of the first quantum computers out there. And So just to look at this molecule from my perspective, this molecule features all of the same attributes that the molecules that we're working with have. So this organometallic, meaning a molecule that has a metal carbon bond, features 7 individual qubits. Each of those qubits is a nuclear spin on an atom. And using a 300 pulse sequence in a commercial NMR spectrometer, this team of physicists and mathematicians were able to implement Shor's algorithm and factor the number 15. Now, this achievement is well known to everyone in this audience, but what I want to highlight here are the things that make this molecule an awesome quantum computer. So first of all, every single molecule in this NMR tube is completely identical, down to sub-angstrom precision. You can place these fluorine atoms exactly where you want them, and those distances are also precise, down to sub-angstrom precision. And finally, you can tune this molecule, and well, you can't magically add another fluorine here, which is why we work with electronic spins and not nuclear spins in my lab. But you can add additional spins as you want. And so all of those features make molecules very well suited to different quantum applications where you want precisely controlled systems. And I'll just throw in, as a chemist, how much fun it is to be in this field. This is from the abstract of the paper, which was helpfully communicating quantum information science to the broad field, and explained that the prime factors of 15 are 3 and 5. And I love this. I love that because this is such a fundamentally interdisciplinary field, we have to take a step back and ensure that everyone is communicating on the same level. And that actually reduces the barrier for entry in a beautiful way. And so I would just like to put in a plug for continuing with these very basic conversations, because that helps me as a scientist, and hopefully it helps others. And as you'll see, I'll be communicating at the chemistry from what I see as a fundamental level. Okay, so why is synthetic chemistry awesome, and what approach do we take? So similar to that organometallic molecule, we work on transition metal complexes. And so transition metal complexes give us a large number of handles to play with. We can modify the identity of the metal. We can change the ligands, that is the things bound to the metal, right, the organic moieties. By changing the ligands, we modulate the ligand field. I'll be going into this in a lot more detail in maybe 40 slides, but by modifying the ligand field, we change the energetics of the d orbitals. And changing the energetics of the d orbitals enables us to both manipulate the ground state electronic structure and the excited state manifold. And having that level of control is really powerful. Finally, we can change the spin delocalization, which has a significant impact in qubit-qubit interactions. So not only can we modify the intrinsic properties of these systems, we can also modify the extrinsic properties. So the way that I would describe this is if you're thinking about another spin-based qubit, for example, the anionic nitrogen vacancy pair defects in diamond, this is like saying you magically remove the diamond and put it in another environment. And so that's powerful, both from a fundamental insight perspective, but also for applications like quantum sensing, where we want to be able to think about ways we can embed these systems in different matrices that are appropriate for various applications. So we can also play around with charge matrices, as I was just describing. And finally, we can connect these individual spin systems to each other using framework chemistry in an analogous way to the covalent interactions in that beautiful quantum computing example from 30 years ago. Okay, so I'm gonna talk about 4 brief stories. One is how we can use chemistry to gain fundamental understanding of these systems. And I'll show a series of molecules that we made, which we think of as rulers. Another very brief story is, can molecules have respectable coherence times? And then I'll talk about how we can bridge chemistry and atomic physics. Round 1, hopefully in the future we'll have round 2 on that. And finally, I'll talk about making molecular analogues of color centers. And so enabling molecules to be optically read out. Okay, So molecules are awesome because we can just put atoms where we want, right? So one fundamental question that we wanted to look at is, how does the proximity of a nuclear spin to an electronic spin impact the coherence of an electronic spin? And so to do that, we go back to our periodic table and we just build. Chemistry is so much fun. So we decided to take vanadium, which has a nice S equals 1/2, which has the potential to host a nice S equals 1/2 ground state, and connect it with nuclear spin-free ligands. So there we focused on binary carbon sulfide ligands. And we're really fortunate there because in the field of molecular conductors, there's a deep literature on creating different ligation strategies for binary carbon sulfide ligands. And finally, we punctuated it with a series of protons. So I'll show you the series of molecules on the next slide. But what I want to emphasize here with this periodic table is we can just pick and choose the elements that have no nuclear spin to create a bridge between an electronic spin and a nuclear spin, such that we can cleanly isolate our variables. So my first student, Michael, pictured here, took these vanadium, so vanadium is green here, centers with these binary carbon sulfide ligands and punctuated them with protons. You can see the heavily conjugated nature of the ligand. These are crystal structures, enforces a planar geometry, and that planar geometry maintains the precise distance that we want. So I'm showing the low temperature data, of course, because at high temperature, everything's going to be dominated by phonon modes. So at low temperature, what we observe is that one of these molecules has a significantly longer coherence time than the others. And so initially to us, this was the counterintuitive result, but I suspect that perhaps to this audience, it's not the counterintuitive result. We observed that the system where the protons are proximal to the electronic spin is the one with the longest coherence time. And this is actually a physical measurement of the spin diffusion barrier. And from a hand wavy perspective, which I've animated on the next slide, you have two magnetic moments, your electronic spin and your nuclear spin, and they're flip-flopping and erasing each other's information. If they're really close to each other, the flip-flopping effectively can't happen. And as they get farther away, you get to, as my student Michael put it, a point of maximum badness. And then as you go further away, they influence each other less. And this is a theoretically described concept called the spin diffusion barrier. And this series of molecular rulers enables us to actually measure it. So here's an animation that my former student Raymond made showing the spin diffusion barrier. So we have these environmental nuclear spins that significantly impact decoherence, but then we have effectively these decoherence inactive nuclear spins that are within the spin diffusion barrier. And this is a way to measure it. Now, one really beautiful thing about working in this space is that concepts like the spin diffusion barrier are really important for quantum information science, but they're also important outside of the field. And so an area where this is important is in dynamic nuclear polarization NMR spectroscopy. And there, the 3 order of magnitude larger spin of an electronic spin relative to a nuclear spin is harnessed to polarize nuclear spins to overcome the famous insensitivity of NMR as a technique. Now, one area of development in DNP that would be really cool is endogenous polarization. And so what that means is taking a spin which already exists in your analyte of interest. For example, you can imagine a metal at the center of an enzyme and using that to locally polarize its surrounding environment. That would be powerful because then you can measure the thing that you're actually interested in at the time scale that you're actually interested. But there remain a lot of questions before we can enable endogenous polarization. The first is expanding the catalog of polarizing agents beyond primarily radicals with a handful of examples that aren't radicals, gadolinium, manganese, I'm missing one, but largely radicals. But the other is actually measuring which specific spins are polarized. And understanding which spins are polarized relates back to this concept of the spin diffusion barrier.
Anna,
So,
if I could
oh
interrupt
yeah,
you quick, we have a
please.
question in the chat from Paul.
Oh,
So
sorry.
he asks, oh no, it just showed up. Is the environment here on the same molecule or in surrounding material? So what do you mean by environment?
In particular, and you had the picture with this animation, and you had your molecule in the middle, but then you had the other things around it, which were the environment. But I somehow thought that the environment was supposed to be the protons on the end of your.
It is the protons on the end. Yeah, so you're right. The graphic is a little misleading, but it is the protons on the end. And we also did some additional follow-up and/or studies and an extrinsic environment dependent study to demonstrate that it was really the protons on the molecule and not any other component of the environment. That's a very good point.
So I'm surprised that you don't see a minimum in the, I'm surprised that as the things get far enough away, you don't see the coherence time go back up, because the other things are so far away, I don't even know what's going on at that other end, right?
No, they're right. And so we believe, which is vaguely substantiated by the literature, that we'd have to get one more, here, let me, I'm going to close this, that we'd have to, I don't know if you can see my mouse, but that we'd have to add effectively one more of these cyclic systems to get to the point where it goes back up. I really wanted my students to do this, and they very helpfully, so these molecules are all new, but they very helpfully showed me what the synthetic pathway would be to achieve that. And after seeing what would be required, I said it probably wasn't worth it. It's realistically a multi-month at least synthesis, because there are a lot of purification stages. And as these systems get much longer, you start to have some solubility problems in terms of purification. So we decided not to access the additional one. But yeah, I think that's exactly what you would see if you could get it just a little bit past that 12 angstrom point.
Great, thank you.
Yeah. Shouldn't mute myself. Okay. So exciting to get questions in a Zoom seminar. Okay, so we collaborated with Sunggi Han at UCSB. Sunggi is many things, a DNP expert, instrument builder. She's just a phenomenal scientist and human being. Oh, if you haven't had her for the seminar series, you should have her out. She's just great. And we collaborated with her on using these molecules and seeing if we could determine which protons are the ones polarized. And this is the first step of a roadmap for endogenous polarization. It's also worth noting that polarization from these vanadium-based molecules represent the first example of vanadium-based DNP. And so we did observe polarization based on these. And the take-home point of this slide is that this pink molecule, which had the longest coherence time, where we believe the spins are within the diffusion barrier, indeed did not experience polarization. So it was only molecules 2, 3, and 4 that were able to be polarized. And so this is an important first step to figuring out, if you were to polarize endogenously, where would the protons that you're seeing signal from be? And that would be fantastic for understanding, for example, how a substrate interacts with an enzyme during catalytic turnover. So we're excited about ongoing work in this direction. And I'll just say that our future work will focus on, we have distance. And so the next step is orientation. Is there an orientation dependence to this? And can we look at the inherent difference between parallel and perpendicular components of G in transition metal complexes to exploit this? This is another advantage to moving outside of the sphere of radicals. Okay, so switching gears, we can not just look at nuclear spins and electronic spins, we can look at electronic spin interactions. And I'll say this is a story without too much of a punchline, but one way we can do this is by mimicking the NMR example, which involves frequency addressability. and as opposed to spatial addressability. And so to achieve frequency addressability with transition metal complexes, we're just going to look at systems that have a G significantly below 2 and a G significantly above 2. And we can achieve this by picking from the beginning and the end of the periodic table, or the transition metal series to be specific. And so titanium 3+ and copper 2+ are fantastic examples of metals that will feature significantly different G values just by virtue of their position on the periodic table. And we can take individual units that have each that feature copper and a titanium atom, and we can link them together. And this is work done by a current postdoc in my lab, Stephen. We can link them together and vary the distance between them in a way that's analogous to the electronic spin, nuclear spin example. One really nice thing, which to keep advertising why chemistry is awesome, that we can do with these systems is we can create controls. So we can also have the just copper and the just titanium analogues, which are otherwise structurally very similar to compare. So this is right, this is the analogy of making a diamagnetic analog for your heat capacity measurements. You can make the diamagnetic analog for your EPR measurements. So here what we observe is we can see that the copper in the CW, sorry, physicists, I need to stop saying EPR. In the CW ESR data, we observe that we can spectrally distinguish the copper signature from the titanium signature. These are just simulations done in easy spin. We also can observe Rabi oscillations using a nutation pulse sequence on all of these molecules and demonstrate that they're all S equals 1/2, which is valuable. That tells us that we're effectively operating on the spins independently and that we're not operating on the coupled ground state. So what we observed is that the coherence time of the copper is effectively invariant to the distance between the copper and the titanium, but the coherence time of the titanium increases as it's pushed away from the copper. And functionally, what's happening in this system is that it ends up being limited, not by the electronic spin, coherence limited, I mean, not by the electronic spin interaction, but by the overabundance of nuclear spins. And so this actually connects right back to the previous work that we did, which indicates that unfortunately, the nuclear spins are exactly at this point of maximum badness. And so because of that, the electronic spin interaction doesn't dominate our observation of coherence time. And so this does point the way towards designing further systems. But one thing that's really nice about this is it shows that we can create systems where we have two separate frequency addressable candidate qubits. And so, of course, we'd like to follow up this work, which we haven't, by trying to execute some gate operations. And I'm also happy to talk to any of you about this. Okay, so I'll transition from that to briefly talking about maximizing qubit performance. And this is actually very old work. So one challenge with molecules is that they're really messy, right? And they tend to have significantly shorter coherence times than, for example, the anionic nitrogen vacancy pair defect in diamond. So a question that we had was, can molecules even enter the same range as other candidates? And so to do that, we effectively decided to try to mimic the anionic nitrogen vacancy pair defect in diamond. And so we thought, okay, can we make a nuclear spin-free system and see what coherence times we get? And so my former postdoc, Joe, now an assistant professor at Colorado State, who also gives great talks, took this molecule right here, which you can think of as vanadium encapsulated in this binary carbon sulfide ligand sphere, and acquired some ESR data on it. And so he observed that it has in proteated solvent a coherence time of about 3.5 microseconds. If you deuterate the solvent, it goes up to about 7. So to compare, the analogous nitrogen vacancy pair defects in diamond, that is to say non-isotopically enriched, comparable concentration of defects, etc., is about 600 microseconds. And so this isn't great, right? It's significantly lower, but these are still good numbers. We can work with microseconds. But Joe took this a step further, and he said, okay, well, we have these molecules in these proteated or deuterated solvents. What if instead we actually mimic the diamond in terms of solvent? So what if we put this molecule in a diamond equivalent? And our chemistry, diamond equivalent, is again, this binary carbon sulfide solvent, carbon disulfide. And so carbon disulfide is comparably nuclear spin-free. And what we observed was a significant increase in the coherence time. And these are some beautiful notations. But I'm just going to skip that and say that, if these are the previous data that were plotted, and this is the increase by changing out the extrinsic environment. And if you remove the log scale, it actually looks impressive. And so these numbers are fairly similar to the NV centers. Again, comparable concentration, non-isotopically enriched, et cetera. So to us, what this says is that molecules can be optimized to be within the range of other spin-based qubit candidates. This doesn't mean this molecule in CS2 is going to go into a quantum sensor or anything like that. But to us, it says that careful synthetic optimization can get us into the right range for a number of applications. So that's something that we were relatively excited about. I should say that gets us to 675 microseconds, which I have here, but not on the previous slide. Okay, so after talking about how awesome molecules are in their individual form, one thing that I said at the beginning we could do is create networks of these molecules. And you can imagine creating a network using some form of framework chemistry. And there are a lot of frameworks out there. It's possible that you've even heard of metal organic frameworks, which have been for a while a hot topic in chemistry. But the thing is, metal organic frameworks are really magnetically noisy environments. And so if we want to be able to create, and we also synthesized a lot of these systems and acquired a lot of ESR data and couldn't even get an echo. So we decided to take a step back, and because you're physicists, I'm just going to skip all of this and just say that we decided to see if we could engender a clock-like transition within these systems to increase their coherence time. And I'll be very careful and say clock-like, because of course these systems are incredibly messy and don't have anything resembling a pure transition in them. So how do we get a clock-like transition in a molecular system? That gets us straight back to chemistry, which is the fun part. So what we want is we want a simple system where we have S equals 1/2 coupled with an element it can mix with. So we'll take a nuclear spin. A nice pure I equals 7/2 would be fantastic. So we want a large nuclear spin and we want a large hyperfine coupling parameter. We want that so we can have a wide spread of transitions and have one transition that can serve as an internal control, a Zeeman-like transition, and one transition probably at low field in the strong mixing regime, which is going to be a more clock-like transition. Okay, so how do we get this? So we can think immediately of cobalt 2, which is almost purely I equals 7/2. And cobalt 2 plus is has an odd number of electrons, meaning that you can get an S equals 1/2 state. The problem is most cobalt 2 complexes, like the vast majority of cobalt 2 complexes, are high spin, meaning S equals 3/2. But if you put your cobalt into a porphyrin, which is a fantastic and ubiquitous chemical structure, you get a low spin configuration. And not only do you get a low spin configuration, you get a low spin configuration where your unpaired spin, that is your single electron, resides in the dz squared orbital. And this is fantastic because your dz squared orbital will hybridize by symmetry with your 4s orbital, thereby throwing your spin density really close to the nucleus and giving you a gigantic hyperfine coupling parameter, fulfilling all of our requirements. Okay, so then we need to just throw porphyrin into some sort of framework. And there are a lot of metal organic frameworks out there, and they all have utterly ridiculous names. This is PCN 224, which was initially reported by Zhou Zhao and co-workers at Texas A&M. And PCN 224 features this specific motif that we're looking for, which is fantastic. Previous work demonstrated that the hyperfine coupling parameter is indeed very large. So we, Joe again, took this system or synthesized this system and using easy spin, simulated that at low frequency, these data were acquired at the UIUC EPR facility. So at 3.6 gigahertz, which is a convenient spectrometer available at the UIUC EPR facility, and was wonderful to use, thank you. We can see that there's one internal transition that would be clock-like, and another transition that we would expect to be Zeeman-like. And so Joe acquired pulse data and determined that indeed this clock-like transition, first we can measure it, which was a huge victory, lives for about an order of magnitude longer than the internal control Zeeman-like transition, demonstrating that this is an approach that we can use to measure networks of these molecular spins. Okay. So with that, I'll devote the last bit of my talk to discussing readout. So, one challenge with molecules is readout. And if molecules are going to meet their promise, or at least the promise I've talked about in the first part of this talk, we need a way to move from ensembles of spins, which is everything I'm speaking about in this talk, down to the single spin level. And functionally, there are two ways to do this. One is electrically detected methods, including a beautiful recent report of STM ESR measurements on a single molecule. And the other is optically detected readout. And so I'm going to talk about progressing molecules towards optically detected readout. Now, okay, so I've talked a lot about the anionic nitrogen vacancy, pair defect, and diamond. And I know that most people don't call it the anionic nitrogen vacancy, pair defect, and diamond, but I'm a chemist, so that's what we're going to call it. Now, it matters that it's anionic, of course, because that's how we get the S=1 state. This defect is fantastic, not just because of its long coherence time, but also because you can read out spin information optically. If, what I like to say to non-physics audiences is that the physicists who work in this area are spectroscopists, and they've built up an impressive infrastructure for measuring these defects. But physicists don't synthesize these diamonds. De Beers synthesizes these diamonds. So if we could create a system that couples optical readout of spin with structural precision and tunability, including frequency tunability, or sorry, everything's frequency, including emission tunability, that would be really powerful. And that would seamlessly integrate with the established infrastructure. And this is something I view as a collaborative, not competitive endeavor, if hopefully that resonates with you. Yes, resonates was a joke. I really dislike that people don't laugh at Zoom seminars. Anyway, to create this, the most intuitive thing to do is to look at the physical structure and to try to replicate it in a molecular form. But this defect makes absolutely no sense chemically, right? This is, you have an sp3 carbon, which is S=1. That doesn't make sense. That's not the way that electrons work. That's not the way organic chemistry works. And that's also why these defects have to be buried deep within a diamond to maintain their integrity. You're exploiting the fact that diamond has a low defect mobility and that there's no way for this defect to structurally decompose once it's deep within the diamond. The second you push the defect towards the surface, it stops working, right? So if we want to replicate the physical properties of the system, we took a totally different approach. We threw out the physical structure, looked at the electronic structure, which is what actually enables these properties, and used an inverse design approach. So if I, as a synthetic chemist, look at this electronic structure for this defect, well, I don't see an organic molecule. What I see is a transition metal complex, but I always see transition metal complexes. But let's look at this. I see a triplet A ground state, so highly symmetric, S equals 1. I see a small separation between the M sub S plus or minus 1 and the M sub S 0, which enables driving with commercial microwaves. So a small D value, right? I see an optically accessible excitation to another triplet state, and I see an intervening singlet state enabling the spin-selective intersystem crossing process. So, okay, how do we do that? So, okay, let's start with designing the ground state and then move to designing the excited state. We have our atom in outer space. All of our d orbitals are degenerate. We apply a ligand field, and the ligand field moves the d orbitals around and enables different configurations. There are a number of configurations that are amenable to this triplet A ground state shown here. For the octahedral configuration, you want to think about a D8 like nickel 2. And here are some examples. You can imagine a tetrahedral D2 system, where the ligand field perfectly holds these two orbitals at the same energy and maintains this degeneracy. You can imagine a trigonal biparameter, you can imagine a distorted octahedral system where you have this degeneracy, and you can imagine a trigonal bipyramidal system, which would be amenable to a number of different configurations. D2, as shown here, also a D6 configuration would work for this. So you can see that there's a whole number of ligand fields that would support this triplet ground state and the triplet first excited state. So let's go back to our canonical octahedral example to talk about, in all of those configurations, by maintaining the rigorous degeneracy of the spins in the singly occupied orbitals will also hold down your zero field splitting. So let's talk about the excited state. If we want to design the right excited state, manifold, we go back to our canonical octahedral diagram. This also, of course, works for any of the other configurations that I've shown, but it's always easiest to show things on octahedral. So we have our ground state triplet, and so here I'm showing a D8 configuration like nickel 2, and we have our excited state triplet, and this is something that we're going to think about just being accessible through something which is optically accessible by a laser. So we want to think about the right energy there. This gap is dictated by the separation between the lower set of 3 orbitals and the higher, right? The T2G and the EG, your delta OH splitting. And that's because a triplet excitation necessarily involves the promotion of an electron from the T2G to the EG. Your singlet, which you want intervening, does not follow that path because your singlet is a spin flip. And so it'll be effectively invariant to your octahedral splitting. And so your octahedral splitting is effectively a measure of how strong your ligand field is, so how electron donating it is. So if you want to be past this crossing point, you just need something which is a strong field ligand, so ligands that donate a lot. So let's talk about specific systems, and shown here is the specific polarization scheme that I'm going to be talking about. I'll go over it a little bit on the next slide, but I'll just briefly say that we've moved from off-resonant in NVs to a resonant excitation scheme. So there are a number of different ways that we can achieve this. You can imagine a vanadium complex like the ones described above. Vanadium 3 D2 system. you can imagine looking at chromium systems, chromium 4, D2. You can also imagine going to the other end of the periodic table and looking at these D8 complexes that we described. And you can also move from the first row to the second row. So the polarization scheme, and so one thing which is familiar to this audience is that there are a large number of these so-called defects in semiconductors or color centers. Semiconductors is an interesting term, but anyway, these defects in these wide band gap materials. So each of these different defects in wide band gap materials features a different excitation scheme. Here we're looking at a resonant excitation scheme where we pump population out of the m sub s equals 0 state into the plus or minus 1 state and use microwaves to transition population between these levels. And we can read out with photoluminescence. So the design criteria for this are exactly what I articulated before. We need to pass this intersystem crossing point so we can have photoluminescence from the singlet state. We want to minimize our axial zero field splitting for ESR. We also want a sufficiently long T1 for initialization, and that's simply so we don't scramble our information. One way that we can conceptually think about doing this is extracting a color center from a diamond lattice. But really, we're building this up from the ground up. So here we have an organometallic chromium center where, because chromium is bound to carbon, that's also really nice for nuclear spins, for reducing nuclear spins, I mean. And we can trivially modify this chemically. Now, what you can see is we have chromium at the center bound to carbons in a tetrahedral fashion. This is chromium 4 plus D2, so we're fulfilling our criteria. And we can just throw on methyl groups, because this is what we like to do. And by throwing on these minor chemical modifications, we actually significantly modify the properties in a predictable, tunable way. So these are just CW ESR data. And from the CW ESR data, you can see that we can pretty much read off the axial and rhombic zero field splitting parameters. And we can see how these small chemical modifications do things like, for example, turn on our rhombic parameter, which I think is really cool. Not only do we modify our ground state electronic structure, we also modify the excited state structure. And you can see we're tuning the photoluminescence frequency. And I just want to point out that by doing something which is actually simple chemically, I shouldn't say this, I'm not the one in lab doing the work, but it is moving the methyl around. We're changing the emission frequency, which is something that's fairly hard to do with solid state defects. And so we can also recapitulate the ESR data optically, and these data are in collaboration with the Echelon Lab at the University of Chicago. And these data, and the Echelon Lab at the University of Chicago also demonstrated that we can do, that we can acquire all optical T2s and all optical readout data, effectively demonstrating that these molecules are, I'm trying to make this catch on, molecular color centers. Okay, so in conclusion, I just want to say molecules are awesome. We can expand molecules beyond demonstrate this property significantly beyond the 3 molecules that I've shown you here. And hopefully I'll be talking about that at some point in the near future. Molecules could be really awesome for quantum sensing because we can customize them and tune them. And this is a graphic that my student Raymond made, which is, I think, appropriately ridiculous. And I want to thank my students because they do absolutely all the work, funding because they pay my students, and you for your attention. Thank you.
Thanks, Danna. That was awesome. So we'll